Welcome back to the summer school, and we are now ready for Stephane Bonhomme's lecture on unobserved heterogeneity in structural models. Stephane, thank you very much for giving this lecture. Please go ahead. You've got 1.5 hours.
Thank you so much to the organizers. Hi, everyone. I'm sorry I can't be there in person. I had a family emergency to attend to in France. But I'm happy that it's still feasible to give the lecture on Zoom. Please let me know if you have if there are issues with the audio, or of course if you have any questions about the class. Is that good so far? Can you hear me? Yeah. Okay. So my goal in the lecture is to talk about methods to incorporate unobserved heterogeneity in structural models. So this is not about subjective expectations and beliefs. Of course, when we have subjective expectation data or beliefs in our models, issues of unobserved heterogeneity show up greatly. That was one issue that I mentioned in my presentation 2 days ago, the paper with Angela Adonis, where we estimate how beliefs affect decisions. And there, how to account for unobserved heterogeneity is very important. And that often raises, real technical challenges. So I want to go through some methods that have been proposed, some of them a long time ago, some of them more recently, to try to account for unobserved heterogeneity in the best possible way. So the outline, I'm going to first talk about the a representation of a model with unobserved heterogeneity. You will see the basic structure is a mixture structure. And from that mixture, we will be able to think carefully about identification and then develop different strategies for estimation. I think the most standard strategy in the literature is so-called random effect strategy, where we model the distribution of unobserved heterogeneity. So I'm going to talk about that and review some well-known approaches. But then I want to turn to methods that are a bit more recent, so-called group fixed effect estimation, which I believe actually can be very useful in structural context as well. And if time permits, I will go through a few applications just to illustrate the methods. But I anticipate that most of the lecture will be about methods, the methods themselves. Okay. So before I go there, I wanted to kind of give a little bit of motivation for why unobserved heterogeneity is very important. So, there were some very important papers like the King and Wolpin 97 papers, back in the days, showing that actually accounting for unobserved heterogeneity is very meaningful empirically, that it really matters a great deal. Sometimes these unobservables, maybe permanent unobservables at the individual level or the firm level, for example, explain a lot of the overall variation, and you need to account for this variation if you want to have credible results. So, as an anecdote, what I often see in Chicago with our students is kind of two-step process. The first step is to write down a structural model without unobserved heterogeneity. And that one, we can estimate it in a week, maybe. And then the student shows the model to the supervisor. And the supervisor says, yeah, sure, that's nice. But without an observed heterogeneity, nobody is going to believe the results. So then the student goes back to his office or her office and unfortunately needs to work for a year or 2 years to try to incorporate the unobserved heterogeneity. So this is, I think, perhaps not an exaggeration, actually. Accounting for unobserved heterogeneity can increase the burden on the researcher quite a lot. So I hope that the methods that I'm going to review now could help with that, actually, could make all this process a bit less painful and also perhaps more transparent. Okay, so let me start right away with the mixture representation. So think about a very simple single agent, prototypical choice model in a structural setting, right? So think we have a finite horizon. We have some choice variables That's this CT here, and we have some state variables, ST. We have agents have some preferences, utility U, and a discount factor. And then these state variables, they follow some transitions. Okay, so the state today depends on the state yesterday and the action yesterday, right? So a few remarks about that, right? These states could be quite general. For example, they could include beliefs about the a part of the other state variables. For example, you could have income and beliefs about future income as state variables in the model. And this law of motion would include the joint law of motion of the income and the beliefs about future income here. Okay, and right now I have not indicated the presence of heterogeneity, so we can think of this as a model for one person, which I think it's really the way we would think typically. A consumer or perhaps a firm making decisions. And then in this setting, agents are going to maximize expected utility. Okay, and we get a value function, right? So very, very standard dynamic structural type of setting. And based on this, well, under some assumptions, perhaps some of these states include some unobservables, perhaps some normal shocks or some extreme value shocks, and then we can build a likelihood function and we can estimate the model. But the issue is that the model itself, as I was starting to say, is the model itself is not a model that we can take directly to the data. Because in principle, this is a model for one person, and typically we don't have enough data to get reliable estimates for each person in the data. If we did have a very, very long time series, if this T here was finite but very, very large, let's say 1,000 observations, 1,000 time periods, maybe we could hope to try to estimate these parameters, the parameters of the law of motion or the preferences, etc., very precisely. But typically, we don't have that luxury. Maybe T is equal to 10, maybe T is equal to 2 or 3, depending on the application. T could be rather small. So we worry that we can't estimate this model person by person, right? So then the question is, how do we map the model, which is a person-specific model, to our data, which pulls persons together, pulls individuals together, right? And that's where heterogeneity comes in. Right? So in principle, heterogeneity could be, of course, we could say we have a different model for different sectors, or we have different model for different education groups. But we know very well that this is not enough, actually, to account for the meaningful heterogeneity in the data. There are many other dimensions that are heterogeneous, and typically education or sector or different aspects account for a relatively small share of the overall heterogeneity across agents. And here in the talk, mostly, except for maybe 1 or 2 slides, I'm going to focus on time invariant heterogeneity. Right? Heterogeneity that does not vary over time, because it's the simplest case, and it's also something that empirically seems to be very important to account for anyway. So it seems like a very important first step. Relaxing the assumption that heterogeneity doesn't vary over time is challenging, might be important in some applications, but perhaps we can see that as the next step in the agenda, right? And so the goal here would be to focus on permanent heterogeneity. So actually, let's think about heterogeneity here. We could think heterogeneity affecting all the different elements of this model, right? Potentially, people could have different preferences. They could have different discount factors. Their beliefs could also be heterogeneous. The law of motion of beliefs, right? If beliefs are in the state variables here, the law of motion of these beliefs, the belief formation process, could also be different for different individuals, right? And other state transitions could also be heterogeneous. For example, there could be agents could have heterogeneous returns to wealth, right? There is a growing literature on that actually empirically, right? So all of this heterogeneity could be there. And again, here we're thinking about permanent unobserved heterogeneity just because it's simpler to study. Yeah. And the bullet point here is about the fact that we know this heterogeneity matters a great deal. And if we think about, again, making everything completely heterogeneous, then we very quickly hit a wall you know, we hit a very severe constraint that we can't really make useful progress because we don't have enough data. So we're going to make an assumption about heterogeneity. And an assumption that is very common in the structural literature is to assume that the heterogeneity takes the form of discrete types. Okay? So what is a type? Well, suppose you have your agents, right? Let's say an individual or a firm. Let's say about a worker to be specific. That worker has a type A. And this type belongs to K values. Actually, these K values could be 1, 2, 3, 4 to K, right? The way we call them is really not very important. So there are type 1 individuals, type 2 individuals, and type 3 individuals. Let's say if big K is equal to 3. Here we think of this K as being small, much smaller than the number of individuals or workers in the data set. And this type modeling is interesting because it gives us a way to model multivariate heterogeneity. I really think this is one of the leading reasons why type approaches have become very popular in structural work for a long time. Because if we think about the type, right, then we can deal with extremely rich form of heterogeneity in the data. Let me try to be more specific. Let's go back to the model, the structural model here, with all these primitive objects, right? The preferences, discounting, law of motion, etc. Well, if you're making a type assumption, you're saying there are 3 types. We can say that agents differ along all of these dimensions in terms of their types. We can say type 1 individuals have their own utility function, U1, they have their own discount factor, beta 1, they have their own law of motion of state, let's say pi 1, etc., etc. Okay? And same thing for type 2 and type 3 people. So this means that even though the type itself is very parsimonious, because it's either your type 1 or type 2 or type 3, there's no other possible variation here. The way the type expresses itself in the model can be very rich, right? There can be many dimensions in the model that differ across the type, the dimension of the type. And this is really a very useful modeling device. Of course, this is at the cost of a very strong assumption that heterogeneity can be summarized by these types. If preferences and discounting and so on were heterogeneous and continuously distributed, we would face very quickly a very big curse of dimensionality, try to approximate this heterogeneity. But the type modeling is kind of a very crude way, but useful way to try to address this curse of dimensionality. Okay. So this is the point here, right? The utility here would be UA, right? For example, U1 or U2 or U3, depending on the type that you are. So the issue with continuous type modeling, which I think is very interesting, it's more realistic. Why is it more realistic? Because in addition to between type variation, it allows for within type variation, right? So this is better, of course. Maybe types do not explain that much of the actual heterogeneity in the data. But modeling types as continuous raises lots of challenges. A big challenge is the curse of dimensionality. You need to restrict yourself to a scalar, or maybe at most to a bivariate distribution if you want to do a good job. Okay, so this is something that is important here. So I'm going to focus mostly on discrete type approaches here. Okay, so given this, actually, we're ready to see the structure of a model with heterogeneity. It's a very simple statistical structure, and I think it's useful to see this structure to kind of try to get simple intuitions about how to deal with heterogeneity in practice. Right? And for that, I'm going to simplify the notation, try to make it very compact at the cost of becoming a little bit more abstract. Right? I'm not going to carry over all the notation from the structural model. I'm going to put all the endogenous variables in the variable y here. So what does that include? Choices, of course, choice decisions, but also, endogenous state variables, right? The state variables that, for example, evolve dynamically. Those variables will be in the y if they are dependent on past actions. And there could also be additional pair of variables. In labor context, could be a wage, for example, right? Or profit in the firm context. And X here, so that's the Y. So Y, you think of it as a general outcome, right? And the X will be the conditioning variables. They contain all exogenous variables. There could be some state variables that vary completely exogenously, don't depend on actions. Those one we could put in X. And there could be also, time invariant observable characteristics that we also want to put in X. In addition, we want also to include initial conditions in X, right? That will be also an important part there. And lastly, so we have the Y, the outcome, X, which is the conditioning covariates, and A will be the vector of latent types. And individuals here vary following these latent types. And remember, our assumption is that these types are discrete. They are going to take at most K values. Okay? Think of them as 1, 2, 3, right? These types. And the last object here is theta. Theta contains the structural parameters. And there is something a little bit, important here is that, of course, what are those structural parameters? Let me try to be maybe a little bit more specific because there is a little bit of a jump in abstraction here. Let me go back to the model. In a structural model, suppose that individuals depend vary with respect to their types. So they will have different preferences. These preferences, we can call them, U1 for type 1 and U2 for type 2. Let's say that these preferences can be summarized by the risk aversion of the individual. Let's say gamma 1 and gamma 2. So now we have two parameters that are type specifics. Well, in that case, in the theta parameter here, the vector of structural parameters, we're going to include both gamma 1 and gamma 2. Okay, so I want really to be very specific about that. Okay, so this theta will include the type-specific parameters here. And then what we can write here is this, equation, which I think is very important. It's very, very simple, but it's key to understand what's going on. This is simply the law of total probability. There is nothing more complicated than that here. What this says that the probability of your outcome, remember the choices and dynamic state variables and payoffs, conditional on the conditioning covariates, this probability is the sum over types of the probability of the type given the covariate times the probability of the choice given the covariate on the type. Again, simply the law of total probability. Typically, this sum just takes, a handful of elements, maybe three types. Okay, if the number of types big K is equal to 3. So here we see the theta parameters, the structural parameters will be here. So we have two types of parameters if we want, right? We have the theta and we have the type probabilities, right? These type probabilities, potentially they depend on X. And I want to make one pause about that, to pause a little bit and to comment on this dependence. It's very important to correlate the types with everything that is exogenous in the model, in particular initial conditions. Jim Heckman warned us a long time ago that if you did not condition on initial conditions, you could get very important biases in structural estimation and other type of dynamic estimation. I think this is a very important point. So each time you include latent types in your model, don't assume that they are independent of the conditioning variables, unless you have a good reason for doing so. For example, if in the conditioning variable there is an experiment, there is a randomized treatment, maybe we can assume, right, that the type and the randomized treatment are independent of each other. But the point is that assuming independence with respect to one component of X is like an exclusion restriction. It's actually an exclusion restriction. And that has a lot of identifying content. So we want to be very careful and in general try to flexibly capture how the type depends on conditioning covariates. Okay. So what is interesting here also in this equation, in this compact equation, is that the left, of course, it's identified, it's the data, right? This is simply, if we adjust choices, this would be the conditional choice probabilities. Yeah, is there a question?
I have a question.
Yeah.
Yeah, so this would be what we'd call a correlated random effects approach, right? So
absolutely, that's right.
Types are random effect.
That's right, exactly. This is correlated random effect. And the preaching that I was doing here was do correlate to a random effect. Don't leave them independent, ever, right? Unless you have a very, very good reason for doing so. Yeah.
But correlated random effects and fixed effects, like these are orthogonal to whether the types are continuous or discrete, right?
That's right, exactly. Actually, we're going to see when we talk about group fixed effect, we're going to see a fixed effect approach with discrete types.
Okay.
Yeah,
okay, great.
that's
Thanks.
right. Absolutely. Yep. So the left-hand side here are the CCPs, right? Not conditional on the type, right? The marginal CCPs. Those are data objects. You could estimate them in the data if you wanted to. On the right-hand side, then you have the parameters of the model. You have the theta. The theta, typically what we have here is a fully parametric model, right? Why do we have fully parametric models in structural models? Because we want to go for counterfactuals. So, that's the reason why we like to have a full structure here very, very often. So if we have a parametric model, then, if I knew theta, then I could generate observations from the model given your type. Right? I could generate all the choices, etc., dynamically. So that's the subject here. And the theta is the first set of parameters. And the other set of parameters are the type probabilities, right? So on the right-hand side, you have the parameters. On the left-hand side, you have the data. Okay, so it's kind of a very clean separation here. So in compact form, we can be a little bit more abstract even. And why this? We recognize a linear system for given theta. What do I mean by that? On the left, what we have is the vector of CCPs, of conditional choice probabilities, that I call here dx for a given x, right? Those are just the probabilities for different sequences of outcomes, sequences of choice, etc. We are putting all of these probabilities into a big vector. Okay. And on the right, so that's the data. Those are the CCPs. On the right, what do we have? We have the vector of type probabilities. Again, maybe it takes 3 elements if we have 3 types. That actually sum to 1. Okay? Because those are probabilities. This would be the P. And this matrix would have as many rows as the number of outcome sequences, and as many columns as number of types. For example, 3 columns. Okay, this matrix M here. M is specific to a given X, a given covariate here. All the argument would be conditional on X. There is no problem. And it depends on theta, of course. A different theta will generate a different vector of CCPs. But a different pi will also generate a different vector of CCPs. Okay. But the point here is that given theta, this is simply a linear model. So then we can actually exploit that linearity to analyze identification and also for estimation, actually. So this, we can think of the data vector. That's why I call it D. And this as the model matrix. That's why I call it M. Okay, this is the model because this transforms the vector of the distribution of heterogeneity into a vector of outcomes. Okay, so of outcome probabilities. Is the notation clear, right? Data is model times the distribution of heterogeneity. So from this representation, that's really the basic representation, very, very compact and simple. We can think about identification. Again, I'd like to go through that a little bit here. Not in a super long detail, but there is more detail in the slide than what I'm going to go through in the presentation. So for identification, the first question I think here is how can we identify theta, right? And it's not completely obvious because although we observe the vector of data probabilities, right? The D here is observed in the data, it's identified from a large population. We don't know theta and we don't know pi. Okay, so because we don't know the pi, it's hard to get a direct mapping between theta and the data. But here's the key. The key is that because this system is linear in pi, we can still actually get useful restrictions. And that's an insight that actually I use in a paper that is called the functional differencing. And I think this type of thinking can be useful in these structural settings as well. Let me try to be a bit more specific, right? Let's try to step back a little bit before we go there. Remember, the model is not at all linear in the type here, right? Actually, the types are discrete. So we can't difference out the type as we would difference out a fixed effect in a linear panel data model. But the thing that is nice here is because with the low total probability that we've written, like that famous, equation here, that mixture representation, actually, the model is linear in the distribution of probability, in the type probabilities. It's not linear in the type, but it's linear in the type probabilities. And that linearity is great because when something is linear, you can difference it out. Well, it's not exactly as in your standard panel data model where you would just, difference out two periods. It's a little bit more complicated. We have to use a little bit of algebra. And here is the idea. You start with this equation. And then what you do is that you difference out pi by using a projection. That projection, I'm sure you remember that from your first year of statistics or econometrics. This is the residual making matrix in OLS. This is the identity minus m prime m minus 1, m prime. Okay? This is the matrix that actually constructs elements in the null space of M. Okay? That will be orthogonal to the columns of M here. Okay? And here this dagger is just a notation to talk about absolute inverse. It's a technicality. When we do M prime M minus 1 M prime, actually we don't need the M prime M to be invertible. If it's not invertible, the projection is still well defined. That's why I write this esoteric sign here. It's not very important at this stage. But what we get actually is restrictions now, you see, that are such that this matrix is such that when you multiply this matrix by M, you get 0. You can check that. This is true by the property of projectors. So if we take this matrix and multiply it by D, it's also equal to 0. You see that, right? Because you left multiply. So you get this matrix multiplied by M multiplied by pi. But this matrix multiplied by M is equal to 0. So this matrix multiplied by D is equal to 0. And that actually seems like very kind of a little bit boring and technical, but look at this equation. That equation no longer depends on pi. And that's kind of the key because now we get restrictions directly on the structural parameters, the thetas. We don't need the type probability, the other parameters, the type probabilities. Right, they are no longer there. And then we can study identification based on this type of systems. Actually, what we can get from this type of restrictions, which looks a bit unconventional because it's all using these matrices, we can transform that, and there's a little bit of calculation here, into restrictions. Actually, this is very easy. What is a little bit tricky here is to exactly see how to transform these matrices of probabilities into expectations. But this is explained here in these two lines. But it turns out that this is possible to do that because at the end of the day, we're manipulating probabilities. So by manipulating them in the right way, we get expectations. And the nice thing with an expectation is that we get functions, phi here, that have mean 0 and that only depends on theta. That's useful for identification because we have GMM now. We can think of identification in GMM, local and global identification. It's also useful for estimation because we can think of doing some kind of GMM estimation here. Okay. Although this is not very common in the structural literature, we could try to do that. One remark about
Wait a second.
Yeah.
Sorry. Does identification rely on correctly specifying the number of types?
Yeah, absolutely. The construction here of this matrix, it depends on the matrix M, and the matrix M depends on the number of types that you have specified. Yeah. So, I don't know exactly when to mention the tricky issue of the number of types. This is a bit the Achilles heel of this approach. Okay, so the way the literature has approached that is trying to find ways to estimate the number of types using information criteria, using sequential testing ideas. There are lots of methods in the literature. My reading of that literature, which is actually still very active in statistics, is a bit negative. Is that it's often difficult to find methods that work very well. Typically, what we have are different methods that are justified similarly asymptotically, but give different results in finite sample. And that makes me a little bit uneasy. So I see this test or this as diagnostic, or these methods, these estimators of number of types as agnostic, as a diagnostic, sorry, but not a full proof that we have really recovered the right number of type. So for me, when applying type methods, I think it's very important to do robustness checks and vary the number of types quite extensively. And actually, it turns out that for some methods that we're going to see, doing this type of robustness checks can be very expensive. Using other methods that can be cheaper. That's also a justification or motivation for looking at computationally simpler methods that allow you to explore more broadly what would be the impact of the number of types. I really believe this is important, actually. And this is not an issue that is easy to address and to get, oh, I know exactly that there are 3 types in the data, right? This is not something that in my work I have found ever, okay? So I would think that exploring a range of values of the number of types is very important in practice. But here, this is clearly an argument that is conditional on the number of types. Right. That's a very good point, yeah, absolutely.
And if you, so for example, suppose that there are 10 types and you say there's 2, right? Yeah. Are you estimating some kind of, I don't know, average probability, or are you like potentially getting random numbers that have nothing to do?
Yeah. I haven't seen a formal paper about that. What I know is, of course, the Hall-White result in maximum likelihood, which tells you that you're going to minimize the Kullback-Leibler divergence. Yeah. Right. This is, I think, we're always back to that in nonlinear settings. Whether this is an interpretable pseudo-true value or not, I'm not so sure.
Okay.
Yeah. Okay. Yeah. So that's why, and remember here, there is also the issue that, of course, in reduced form, in definitive, for example, we think about weighted averages, right? But here we're doing structural work. For structural work, we can't allow for pseudo-true values. We don't have this luxury. We need the true value. So we want to do the counterfactuals in the end. We don't want to get a number that is a weighted average of stuff. So I think that's also, raises the bar a little bit in what we need to achieve. And that's why the number of types is so important as well. But what you're saying, what you're asking is a very interesting question. And again, I've not seen like a formal work on that. Yeah. So in terms of identification, let me say something more. I don't want to go too far because of lack of time on identification, but there is one intuition that is very important here that could also take a little bit out of the abstraction in these equations. If we go back to the linear system, this one, which is really here the key, right? What we're doing here is that we're basically differencing out the pi, okay? Well, what we're exploiting for this differencing to work is that there is more information in the outcome than in the types themselves, in a sense. What do I mean by that? If we want this differencing, this residual, to be non-zero, to be informative potentially about theta, we need the M matrix here to be, I'm trying here to show, I don't know if you see my hands, but like a matrix with many rows and very few columns. This is the good situation, right? The good situation is when the number of columns is small and the number of rows is large. Why? Because intuitively in that case, we have over-identification of pi. We could get the pi, which is, let's say, 3 numbers if we have 3 columns, in many ways because we have many rows. And because we have over-identification of the pi given theta, we get restrictions on theta. This is really the key here. If the matrix M was, on the other hand, a matrix that has more columns, many more columns than rows, then we would be in trouble. Because maybe this differencing would give us no information at all, at least in terms of point identification. Let me give you an example. assume that heterogeneity is continuous, right? Continuous heterogeneity is very interesting. In discrete choice, continuous heterogeneity is challenging, right? Because continuous heterogeneity in discrete choice, we have a finite number of rows because we have a discrete choice. But we have a continuum of columns because we have continuous heterogeneity. So in that case, we don't expect actually this differencing to give us anything informative about theta. We might just end with the famous identity 0 is equal to 0, which we cannot use at all for anything, identification or estimation. So the richness of the outcome here is very important, meaning you need quite, you need the more periods you have, the better. The more outcomes you have, the better. Right? You need outcomes that share the same heterogeneity. And what is nice in these structural settings is that this is actually the way we think about these types. These types, the same type is going to be reflected differently in different outcomes. Then we pull these outcomes together and get information about the type. But the point is we need to have a richer information on the left-hand side in the data, the rows, than in the heterogeneity, the columns of M. Okay, this is really the intuition here. Let me skip this technical thing about pseudo-inverses. And let me just say that, oh, we can also recover the pi here. Actually, if we knew the theta, this is simply this equation, a little bit of an esoteric way again, in writing OLS. This is just M prime M minus 1 M prime D. Okay? Because the system is linear, we can always recover that in terms of identification. However, in that case, we're requiring for this to really give us pi, we're requiring M to be full column rank. Again, pointing to this idea that we need to have fewer columns than rows, right? So that the columns of M are linearly independent. Okay.
I have a question.
Yeah.
When we recover theta, where is it that we sort of make it so that the unobservable types are not capturing all the variation? In the sense of we could have that, we have some 80% have preference for quality and 20% doesn't. We don't want all of that preference for quality be captured by the unobservable types rather than a beta parameter on their quality.
Yeah, that's right. That's right.
We want to minimize the size of the unobservable types. Where is it that we do that?
Well, I mean, I'm not sure we want to minimize. We want really to estimate the structure that we have, which is this probabilistic structure here. So, in an identification sense, we want to think about how from the left-hand side to infer the elements on the right-hand side, depending on that structure. I think maybe what you're wondering is perhaps the pi could be too rich and could explain the whole data itself. And that, yes, I think it's exactly the question of related to over-identification. If the pi is too rich, if the pi is continuous, for example, it's a continuous density, then perhaps I will, irrespective of theta, I will always be able to fit the data with my unobserved types.
Yeah.
Right? This is really the key. So we need that not to happen. In the functional differencing paper, I call that a condition of non-surjectivity. Right? The map that maps heterogeneity to data cannot be surjective. It cannot be onto. If it's surjective, then you can explain everything using heterogeneity. You don't need theta. So theta is not identified. So here we're requiring this surjectivity to fail, right? Which is exactly this idea that we need very few types, right? If we had a lot of types, then we might actually be able to fit the data very well without the theta, and then we're in trouble, right?
Yeah.
Just because we have a lack of identification.
Yeah.
Okay. In the slides you will see there's another strategy for identification. Just want to mention it very quickly. I don't want to go into the math because it's a little bit technical, but this is a strategy that actually does not rely on a parametric model. That's why I think it's interesting also to mention it. Also, it's a strategy that I have seen used in structural models as a first step to study identification and also to do estimation, actually, in quite a few papers recently. And the strategy is that instead of having this structure, remember this structure here, what we had was a parametric model given the heterogeneity, and then the type probabilities, right? This was the structure here. This requires parametric model. Okay, this is a strong assumption. What if we want to relax the parametric assumptions? What the literature has looked at is an assumption of conditional independence. And this is the so-called Kotlarski type of intuitions and, repeated measurements type of models that has been developed in the literature on measurement error. Yin-Yao Hu, Susan Shenak, and many other people have made seminal contributions to that literature. And the idea there is to say, suppose that outcomes are conditionally independent, conditional on the type. So, of course, the outcomes, the choices, for example, will be dependent. But maybe if I fix the type, then I have independence. And that will hold in some dynamic models, for example, with a hidden Markov structure. There will be some structures of this type where you can actually exploit these conditional independence. And the point is that here you don't need actually parametric restrictions. So you can get very powerful identification results that only rely on this decomposition here. And the fact that I'm writing 3 outcomes, 1, 2, 3, right, is not a coincidence. It's what you need for identification, for non-parametric identification in a nonlinear model. So I wanted to point that out to you because I think this is a very useful identification strategy that has lots of applications in structural settings. Okay, I do think that all these non-parametric arguments usually are more thought of as first steps because in the end, in structural work, we want to be able to do counterfactuals. So having a fully specified parametric model is important in the end. But in terms of analyzing identification and trying to relax assumptions, I think this is a very useful type of setting, and I will elaborate on that in the slides for those of you who are interested. Okay, I'd like to spend a bit more time on estimation today, and given lack of time, I don't want to talk too much about this identification strategy, but I will be happy to discuss if you wish. Okay, so there is more material on that here. Okay, I do want to make a few remarks before we turn to estimation. Okay, one is related to what I was saying about correlating the covariates and the unobserved heterogeneity. Suppose we don't do that. Suppose we write this equation here. Maybe we've all done that at some point. We forgot to condition the type on X. What if we take that seriously? What does that mean here? Well, this equation implies that we're assuming that A and X are independent of each other, that the types are independent of the conditioning covariates. If we believe that this is the case, then actually this type of restriction has a lot of identifying content. And I want to make the argument a little bit more precise now that we've seen the mixture representation. Remember, in the mixture representation, sorry, I'm jumping a little bit, we had this model, right? The linear model that was for given X. So for given X, we had maybe 3 outcomes, let's say. So D, or maybe 5 outcomes, and D at dimension 5, M at dimension 5 times 3, right? And we were trying to get restrictions on theta, conditional on X. Okay. And the reason to condition on X here is that the type probability is conditional on X. It's not unconditional. Okay. But suppose that we assume that A and X are independent of each other. Then what we can do, you see this? We can pull everything across X's as well. Now we're going to take the CCPs that are conditional on X, but we're going to pull them, to stack them together across X's. Now we get a D vector that is the vector of conditional search probabilities for all X values in the support of X. We get a giant vector. Right now the dimension is number of outcomes times the dimension of X. Or the support of X, actually. I call that the dimension, is actually the support of X. Sorry. And pi is simply the number of types here. Pi is simply dimension 3. It's not conditional on X anymore. You see that what we have achieved with this assumption is that now the rows of M, we have many more because of the support of X, right? If X has a support 10, then we have 10 times more rows than before. But the number of columns is the same. We still have 3 columns. So now we gain in terms of identification, right? So in this sense, I think that gives a very concrete sense in which this independence assumption, that the type and X are independent of each other, have strong identifying content. If you believe this is true, then that's very useful. One area in structural work where this type of assumptions has been used is when the law of motion of dynamic state variables do not depend on heterogeneity. For example, think of a budget constraint. Think that assets depend on past assets, income, and consumption. But suppose this dependence is the same for different types. The types do not enter the budget constraint. People have the identical returns to their wealth, for example, to their assets. In that case, you can actually use this type of homogeneity restriction to exploit, to get this form of representation that gives you extra variation relative to the case of correlated heterogeneity. This type of homogeneous law of motion is akin to an assumption of uncorrelated exogeneity. And you can use it as such for identification. That's what Kasahara and Shimotsu did in a seminal paper a long time ago, actually, showing how to exploit the identifying power of covariates. Okay, let me mention very quickly 2 extensions that I'm not going to treat, just to give you some pointers. Lots of reasons in economics to let unobserved heterogeneity vary over time. Could be human capital, for example, could be firm productivity, workers' effort, etc. And there is a literature trying to develop identification conditions and estimation under time-varying heterogeneity. A typical assumption is a Markov type of assumption. And here I'm writing a Markovian assumption that you would give you a hidden Markov structure. And hidden Markov has lots of powerful properties that you can exploit. Uon Shum and Arcidia Economiller would be like important papers in that literature. So I don't want to say more because that would take us too far. But I think it's important to notice. And in terms of the techniques, it's actually not that different because we still have mixture representations. It's just that now the mixture itself is more complicated because heterogeneity varies over time. And the way we deal with that is through some kind of recursive expressions. And I recommend, if you don't know, you're new to hidden Markov models, I recommend this tutorial by Rabiner. It's very, very old, but it's very good. He explains everything about Baum-Welch and Viterbi and all the intuitions in hidden Markov, which I think is very relevant for structural work, actually. Okay, that's time-varying heterogeneity. The other extension is, of course, continuous heterogeneity. And I don't want to say much about this. Again, pointers to the literature. With continuous heterogeneity, this system is actually still the same, surprisingly. You still can write this mixture representation. But of course, with continuous heterogeneity now, pi is a density. So it's an infinite dimensional object. And M is not a matrix anymore, it's an operator. It's a kind of an infinite dimensional matrix. So that causes lots of headaches for identification and estimation. We need, of course, M to have independent columns, right? What does that mean if M has continuous number of columns, right? That's the so-called completeness condition. So lots of issues with infinite dimensions when you have continuous heterogeneity. Again, I would stick to the type approach, pointing you to work by Suzanne Schenak, Inyaohu, and others on this for this literature. Okay, do you have questions, or should I just turn to estimation?
I have a question on time-varying heterogeneity.
Yeah.
I mean, it's basically the same question I've asked before, but this time on time varying. So suppose that again, true heterogeneity is time varying, and you assume it's time invariant. Is so, for example, I don't know, human capital through the life cycle, right? Again, this is potentially completely random numbers and not like a weighted average of stuff, which I know we don't want, but
I mean, I think that's right. I mean, I think people have studied this in much simpler models, like in linear models, in panel data. Like the new difference in difference literature is a little bit along those lines. If I assume that the beta I varies over I, but not T, the true beta varies also across time, what do I recover? What kind of weighted average do I recover?
I think potentially something random.
I mean, this type of cases of structural models, I think this is much harder.
Yeah.
You know, to me, this is actually a major worry, right? In some literatures. Let me give you an example. It's actually one of the applications of these methods. Suppose you're looking at workers on firms, right? This so-called AKM literature about Kramart-Margolis. You know, I work in Chicago, and I've kind of an issue with telling my colleagues that the worker productivity or ability or heterogeneity is fixed over time, right? If you think about human capital accumulation, there's it's a bit of a stretch to make that assumption. So my attitude to this is try to work with very short panels, to try to alleviate that issue. It doesn't solve it because you still need panel data, you still need variation over time. But you want to work with short panels because over 20 years, assuming that these types of the workers, of the firms also actually, but for the firm it might be easier to deal with. But the type of the worker is constant over 20 years just doesn't seem right to me. Okay. Yeah. So trying to really reduce the length of the panel very much I think is very important. And I think that applies to this AKM literature, but that applies to many other literatures. If we're making an assumption of constant type, we should not have a very long panel. Okay. Or we should deal with that in some ways. Okay.
So you need at least T = 3, but not too big, basically.
Yeah, if it's too big, then maybe you need to go to these time varying approaches. Or another possibility, I'm not sure that I will have time to mention this, but you could also say that you have heterogeneity that is not a random process, a stochastic process like here. Here, this is really, you get a different draw of 80 in every period. But what you could think is that what you have is more like a trend.
Okay.
Right? So the effect could be an interaction between your heterogeneous trend and your heterogeneity and the time trend itself. That time trend could be linear, it doesn't need to be, it could be just a process. With types, I like this modeling because it makes me think of people having different evolutions, different profiles over time, some type-specific profiles. I think of that as a very useful modeling device because it still allows to use methods from time invariant heterogeneity, pulling information across periods in some way, but at the same time reflects the non-stationarity and the time evolution in the data. Of course, if we're a believer of stochastic processes, right? If we think that human capital is really, for example, a stochastic process, and we're getting these draws in each period, then a trend model is not a good model. Okay, so, or not necessarily. So yeah, that's what I can say about that. Yeah.
Thanks. Got a question?
Yeah.
About your functional differencing approach. So essentially, it's about writing the model linear in the heterogeneity and then projecting that out. And projecting the pies.
That's right.
That's the idea.
Yeah, absolutely. And it's not the fact that you write it as linear is actually not an assumption. You've already made that assumption when you wrote the model to start with. There is no extra assumption there. Yeah. It's exploiting the fact that in probability space, the model is linear. It's kind of that's the mixture aspect, right? In terms of if you look at the random variables, the model, the equations of the model is super nonlinear. But if you write it in the probability way, then it's actually linear. Yeah, that's right. Okay, so let me actually turn to estimation. I think I'm not going to be very long on random effects because I assume that you're already familiar partly with that, and there will be more information in the slides. And I might talk a bit more about group fixed effect because you might be less familiar with that. So what is the standard approach to estimation? Well, the standard approach is to add parametric assumptions, right? You will model these type probabilities. Maybe, the probability that you're type 1 given X, type 2 or type 3, follows a multinomial logit model that gives you a particular expression for these type probabilities here. And given that this is parametric, the other part here, we know that is parametric, that's our structural model. And then what we can do is maximum likelihood, right? And, you might be familiar with that literature. There are actually lots of issues with maximum likelihood in this setting. I really don't want to go too much into details here. And also, I'm not the best equipped person. I don't have enough knowledge in all the intricacies of the literature. But there are lots of methods, trying to, starting with straight maximum likelihood, some kind of nested fixed point approaches, going to other approaches that could exploit CCP representations, and so on and so forth. Okay, but all of that with the benchmark there, or the oracle, would be to try to maximize in a way the likelihood function. Right? And the interesting point here is that we're back to a parametric model if we parameterize the type probabilities. So then this is really a random effect approach or correlated random effects approach, because we're really modeling the heterogeneity. For this, we need a model for the type probabilities that is not, of course, innocuous. It's an extra assumption compared to the structural model we started with. A very small remark that I want to make, and maybe it echoes other remarks that others have made in this summer school. Please be careful with local optima. When you have heterogeneity, the objective function is multimodal. It's always multimodal. Okay, it's never concave or convex. So you have to be very careful and explore local optima issues very carefully. I've read so many structural papers where people write, the equations, the likelihood function, and then they say, here are the results. It's very hard for me to trust what's going on here. I want to know how you explore the objective function in practice. This objective function, maybe it's in 20 or 50 dimensions. It's not concave. We're trying to maximize it. What are the guarantees that we have here? Some statisticians and people in machine learning have tried to be quite careful about this, explore these issues, and conclusions are not very positive. Those are very hard problems. And, the mixture aspect actually adds a lot of difficulty. It adds a lot of multimodality potentially. And that's true for, standard, let's say, frequentist estimation methods. But if you go to Bayesian methods like Markov chain Monte Carlo, you have similar issues that are reflected in multimodality of the posterior distribution. So we have to be very careful with that and explore, right? Try many starting values to be really sure that we're getting the right number. It's tempting to stop the search when we get a number that we like. Please don't do that. Continue and try to probe the robustness to other potential starting values. Okay, that can really matter in practice. Okay, what do people, a possibility in this case to do maximum likelihood would be to do EM algorithm. I'm not sure I want to go into the detail of EM. I just mentioned it here because I think it's a very transparent and useful estimation strategy. And I want to point again towards Arcidiacono and Miller as an EM-based method that relies also on a structure that exploits the conditional choice probabilities here. Okay. And I'm not sure, what else do I want to say about this approach here? Okay, let me actually say a little bit more about EM because it will be useful to contrast to this other approach that I'm going to talk about very soon, which is group fixed effects. Let me say just a bit more. I think that will allow us to understand better the comparison between random effect and group fixed effect. So remember, we are in a likelihood setting, one possibility to maximize the likelihood, given a starting value, so you don't get at a global optimum, at a local optimum, be mindful of that, is to use EM. What is EM in a nutshell? So let me just explain that. It's a very intuitive idea where we iterate between two steps, the E step and the M step. Okay. The E step is going to construct posterior distributions of the types. And these objects are going to be very key in any model with an observed heterogeneity. What is a posterior distribution? Look, it's the type probability conditional on the covariate, but also conditional on the data. Conditional on the outcomes as well. Okay? You see these probabilities that depend on the gamma that was indexing the type probabilities, but also on the theta that indexes the structural model, the choices. So in the first step, you compute these probabilities. How can we compute these probabilities? Well, a posterior probabilities by Bayes' rule is proportional to the product of the likelihood and the prior, which is exactly the choice probabilities given the type times the probability of the type. So it's very simple to compute these probabilities. In some models, the type space is complicated and you simulate the types. I think usually with discrete types, you don't need to use simulations because you have an explicit expression for these type probabilities, although it depends on the complexity of the model. But that's the E step. You would get an estimate, actually an expression for these posterior probabilities. And then you go to the M step. And in the M step is very simple. It's as if you observe the types. What do I mean by that? You are going to use these posterior probabilities, use them to impute the types in your data. And given these imputed types, you're going to estimate your model with observed types, as if the types were observed because they have been imputed. How does it work concretely? Using a weighted likelihood expression here. You see, the log likelihood is weighted by these posterior probabilities. So two steps. First step, compute the posterior probability. Second step, you weight your likelihood by the posterior probabilities and estimate the model. That is, you estimate theta as if the types were observed, imputed using these posterior probabilities. And you estimate gamma, which are simply, simply the type probabilities given these imputed types. For example, if I imputed my types using or weighted my data using these posterior probabilities, I'm just going to run a multinomial logit here of my imputed types on the covariates, and that would give me a gamma. And then in EM, you go back and forth between these two steps. You start with candidates values, a starting value for theta and gamma. You compute the posterior. You re-estimate the parameters given the weighted posterior. And you go back, you recompute the posterior, you re-estimate, you recompute the posterior, you re-estimate, and so on until convergence. This is the strategy in EM. Okay? So the idea here is really to try to work with these posterior probabilities all the time. What's the cost here? Well, I think the cost is that these iterations can be very long in practice because you have to estimate or re-estimate your structural model many times. You see that? Each M step requires re-estimating the theta and the gamma. Maybe the gamma is very cheap. Maybe the theta is not cheap at all. And you need to do full structural estimation with observed types, but you need to do that many, many times. And remember, if you're doing things right, you also need to sample many starting values here. So to do this iteration, maybe this iteration will last a day, but you need to run your algorithm for many days across starting values. Perhaps you can parallelize across starting values, as that can help, but it's a source of computational burden, right, in practice. I'm just saying that, in my view, this is something that is very important to do in practice, to explore starting values very extensively. And that is true for EM, but that is true for any type of methods that is dealing with an objective function that has an observed heterogeneity here. Okay. So this is, I would say, the very traditional approach. Parameterize the type probabilities and then estimate the parameters by trying to aim at maximizing the likelihood in one way or another, using EM or using different strategies. And lots of tricks have been proposed in the structural literature about that. Okay. Do you have questions about this random effect part? Okay, let me turn to the perhaps more novel part for everyone now, which is group fixed effect. Okay. And this is something that I think is potentially very useful. It's not without assumptions. It has some restrictive aspects and requires some good data, but it's a method that can really greatly alleviate the burden of allowing for heterogeneity in structural models. And that's why I want to talk about this method here. So the idea seems very similar to this discrete type approach, but it's actually quite different. Okay. So what is the idea here? In the random effect approach and everything that we've done so far, the traditional approach to unobserved heterogeneity in structural models, we think of AI, the type of someone, right, the type of worker AI, as being a draw from a distribution. And what we aim at recovering is parameters of that distribution, right, the type probabilities. In a group fixed effect approach, we're going to think very differently. We're going to think that this AI maybe does not have a distribution, which we don't really care. What we're going to try to do is to try to estimate the parameter AI. Okay? Those are parameters that we're trying to estimate for each worker. That will be the goal. And there is kind of a conceptual difference between this approach and the random effect discrete type approach that we have so far. This actually looks much more like a fixed effect approach. Think of your traditional panel data model. You have an alpha I, right, in your regression, in your panel data regression, and you might try to estimate that alpha I. And if you have lots of time periods, maybe you're going to estimate it well. The difference here with this traditional panel data approach is that here the types are still discrete. AI is still a discrete number. If I have two types, for Mr. I, his type is either 1 or 2. AI is either equal to 1 or equal to 2. It cannot take another value. That's the assumption with two types. With three types, it's either 1 or 2 or 3. There are no other possibilities. And that actually can help with recovering these types. So, in particular, because we're going to treat these types, think in your data, you will have how many parameters? Well, quite many parameters. As many parameters as workers. Very large, right? As many as your sample size, basically. That's the number of types that you're trying to estimate, number of parameters. But each one of these parameters is a discrete object, either 1 or 2 or 3. Right? So that's what we're trying to aim for here. Now, because we're treating this AI now as parameters and trying to estimate the type, then we don't need a model of the heterogeneity. We don't need a probabilistic model of AI. And in some applications, this can be actually very beneficial not to have to model that heterogeneity. Let me give you an example. It took me actually a long time to realize that this was something that was potentially very important. Here in all the applications we have, we're thinking about single agent models, right? So thinking about modeling an individual type given our covariates might not be such a big issue. It's a low-dimensional object. We can try to be quite flexible in that. But suppose now that we're in a different setting. Suppose that we're in a setting that is not single agent, but more like a network setting, very common in structural work. For example, suppose we have a structural model of workers and firms, where workers work in different firms over time, and there is sorting. In that model, the worker types and the firm types potentially are correlated with the network of workers and firms. A firm type might be very different depending on how connected this firm is to other firms, how many movers the firm shares with others, and so on and so forth, and similarly for workers. And modeling that dependence of the type on the network of workers and firms is very difficult. It requires a lot of modeling assumptions. What is nice here, which is exactly what we did in a paper with Thibault Lamadon and Elena Manresa, in the context of workers and firms, is that if we're estimating the types without, and we don't have to model that distribution of the types, then it actually makes our job as an econometrician much easier, because we don't have to build a very complex models of how the type vary across the network, how sorting takes place precisely in that application. Perhaps this, at this stage, remains a little bit abstract because you have not seen the details of these models of workers and firms, but I encourage you to look at this worker firm application in the slide and maybe also in the paper, like a 2019 paper that we have. To me, this is really an application that convinced me that estimating the types can be, without having to model their distributions, can be very beneficial. And something that we can do also, which is interesting, is that we get an estimate of the type for every person, every worker in the economy, or every firm in the economy. What we can do if we have that is that ex post, we can see how these types relate to the characteristics of the firm or the worker. We can correlate that. And this is something that we cannot do with the standard random effect approach. This is really a point that I think is kind of important. In the random effect approach, what we model is the probability of the type, right, given X. Suppose we want to see how A, the type, correlates with another variable that is not in the model, let's say Z. Suppose, for example, I get a firm type, and I want to see how it correlates with value added, but value added is not in my model. I have a model of wages, etc., that does not feature value added. But I'm interested in how the type correlates with value added. Unfortunately, I can't do that unless I include value added in X and I change my model. That's a point that I don't think is well appreciated in practice. People think that you can just compute posterior probabilities and correlate them with value added. That in general is inconsistent. While if we're estimating the type, then we can correlate them with other characteristics without having to change the model and estimating a new model. So I see that kind of a flexibility advantage of this approach. Okay, question. What do we need to estimate these types? And the answer will be we need good data. And I want to formalize that in the next slide. And then the second question would be how do we estimate those types in practice? Okay, that's kind of the two questions that I want to go through right now. First question, what is it in the data that will be good, what will be informative to estimate the types well? Right. The key there is we need the dimension of Y, right, the support of Y, that plays such an important role here. We need it to be quite large. Quite large means maybe not 50 or 100, but at least 10 or 20. This is kind of the intuition here. So if we have a very small number of outcomes, for example, we just have 2 periods of data and the only outcome is consumption, no way with 2 observations I'm going to be able to pin down the type precisely. But if now I have different outcomes, maybe different decisions and different payoff variables over a few periods, maybe this is enough to get enough information about the type. And actually, this situation, I don't think it's rare in structural settings at all. It's quite often that we have quite rich outcome space. And if that's the case, then it's possible to estimate the types quite well. Let me give you an intuition about that, to me is very illuminating. suppose the model is the simplest model you can imagine. It's not a structural model. It's a model when what you observe is an average outcome over time. And that your outcome is type plus a random shock. When we average the outcome, we average the random shock as well. Okay? So suppose the random shock is IID over time. What is the variance of the random shock? It's sigma squared divided by the number of time periods. So of course there is noise. The average outcome is not exactly equal to the type. There is noise, but the magnitude of the noise becomes smaller as the dimension of the outcome increases. Right? This is really the key intuition why we need a richer outcome here to be able to estimate the type well. Now, of course, this is a completely standard setting. What is slightly non-standard here is that the type itself is not a continuous random variable. It's either, it's either 1 or 2 or 3, Suppose we just have 2 types. Then AI, we know that it takes 2 values, either 1 value or another value. Okay? And it turns out that these values, I don't know what we could call them here. We could call them, alpha and beta. Right? So either AI is equal to alpha or it's equal to beta. You just don't know who in the data belongs to which group. Do they belong to type 1 or do they belong to type 2? But you know that these 2 types are associated to alpha or beta for that value here. And what is nice in this setting is that you can actually compute the probability of making a mistake. Suppose we are trying to infer the type, estimate the type. Sometimes we're going to tell that, Mr. X or Mr. I is of type 1, but it turns out that actually we made a mistake and Mr. I is of type 2, or conversely. With what probability do those mistakes happen? Actually, we can compute them, this probability. And this probability takes the following form here. This probability of misclassification. You're misclassifying the type. Think you have 2 types. AI minus AJ here, when you're misclassifying, will be the distance between alpha and beta. Okay? And suppose that alpha is greater than beta. So this is really the distance here. So that number here is positive. You take that number, you divide it by the square root of 2 times the variance, and you take a minus. And then this is the normal CDF here. So what is this expression? This is an expression that tells you that the probability of making a mistake here is going to become smaller and smaller as t increases. Why? As t increases, t will be actually in the numerator here. As t increases, this quantity tends to minus infinity, and the normal CDF of minus infinity tends to 0. The key insight here with this expression under normality is that this convergence to 0 is actually quite fast. It's actually exponentially fast in t, suggesting that you might not need a very, very large number of time periods for these methods to give you reasonable classification accuracy. This is really the key intuition why we think that these methods can be useful to recover the types.
It's also the case for continuous types.
For continuous types, the rate of convergence is much lower. Right? The rate of convergence for continuous types, it's a rate not of classification. You're not classifying a continuous type, but you could think of estimation error. The continuous type is estimated at a rate 1 over the square root of t. But here, the misclassification probability with discrete types actually is vanishingly small at an exponential rate. So the rate of convergence is much faster. Okay. So, this is, of course, a very stylized example, and it's possible to show, we've done that in a paper, that these assumptions can be relaxed to a great extent, not completely, of course. Now, and you still get this type of fast convergence rate. which is really good news, actually, for these methods. Now, it doesn't mean that in practice we should not worry about misclassification, of course, right? As usual, when we're estimating something, the presence of sample noise is the big elephant in the room. We need to deal with that, right? My recommendation when we use these methods is to do Monte Carlo simulations. Trying to set up a Monte Carlo simulation that is not too far from your estimation setting, right? Trying to calibrate it in such a way that it will be very close to your data. And then in that laboratory, in that experiment on your computer, try to compute the misclassification probabilities. Try to see how large they are. And they will differ very much across settings. In some settings, misclassification will be very large. In some settings, it will be very small. For workers on firms, for example, to classify firms, for large firms, we got very, very accurate classification. That's not surprising. For small firms, we got some very poor classification. And you have to think, oh, should I worry about this poor classification? How could I try to address it or alleviate it, and so on and so forth? But setting up a Monte Carlo, I think, is very important potentially here. Okay, so how do we estimate the types here? I don't have a huge amount of time, so I'm going to glance and to skip over the joint estimation because I think this is actually too hard in structural settings. Joint estimation will be to say, let's estimate the structural parameters of the model, the thetas, and the type of every individual together. This is actually very complicated. So I want to point you towards an approach that is much simpler, but that relies on stronger assumptions. Let me show you this approach. This is called two-way fixed effects. Two-way group fixed effects. Oh, sorry, two-step group fixed effects. I don't know, I'm obsessed with two-way fixed effects these days because of difference in differences. This is two-step group fixed effects. And the idea is as follows. Let's try to get the types in the first step. We will not know how these types are reflected in the structural models. For example, we will not know what is the risk aversion of different individuals. But we will be able to partition the set of individuals into types. We will be able to say, look, those firms are type 1, or those other firms in the data are type 2. This is the first step here, and I will go back to this problem. Then the second step is, once we have done this partition of individuals into types, we estimate the structural model. Look, this is the likelihood, but now the type is the estimated type. It's observed. It's like a covariate. So you use any of all these methods that I was mentioning to trying to maximize the likelihood or doing structural estimation with observed types. That step is very easy, and we just do it once. There is no iteration here. We never go back to the first step. You could, if you wanted, as a robustness check. But in principle, this is not needed in the approach. So, of course, in this two-step approach, the difficulty is justifying this first step. And what do we do exactly in that first step? How do we get the types in the first step? So let me try to tell you the motivation. The idea here is that we're in a world with a very structural world where the types are the sources. Forget about covariates for one second. The types are the only reason why people are heterogeneous ex ante. Given this, we expect that if we compute moments of the data for a given individual, for example, the average wage that a firm gives its workers, that average wage should depend on the type, should be a function of the type. If firms differ with respect to their types, and there is no heterogeneity within type. And that motivates an approach that would take a vector of moments. In the case of firms, would be firm-specific moments. In the case of workers, would be worker-specific moments. You take these vectors of moments, and then you use a classification algorithm to put the vectors that look similar in one type and the vectors that look similar to each other in another type, to separate these two sets of vectors. That's done technically by maximizing the between type variance between these moments, or minimizing the within type variance. The algorithm that does this is a so-called k-means algorithm. It's really very much off the shelf. There are lots of issues with k-means that I don't have time to go into. I would be very happy to exchange about that. But the first step is just taking that vector of moments. Let's say you take the average wage that the firm gives its workers, and maybe also the standard deviation for each firm, and you use k-means based on these two things. That will give you a partition of firms. Then in the second step, you use this partition, you never touch it anymore, and estimate your model as if the types were observed. They correspond to that partition. Now you have been able to color the firms. You know which firms are type 1, red, and which firms are type 2, blue. And given these colors, now your job is very simple. You can imagine that there are extra assumptions here that we're making compared to what I've been talking about before. Because now we need to have good moments that are able to pin down the types. And of course, the choice of moments will be model specific. And there is, we need to have a lot of thoughts when we choose moments in practice. But the point is that if we find good moments, then estimation can be much, much easier than this type of sequential EM style, maximum likelihood, random effect style estimation that I was mentioning before. And as a byproduct, we're also able here to estimate the types. Okay, so I'm very happy right now to take questions because I think I went through the group fixed effect approach quite quickly. Yeah, thank you.
We started a little late. I think we can take, some minutes for questions if there are any.
Absolutely.
I was wondering for repeated cross-section data, you have say like large T, but you only have repeated cross-sections. I guess this wouldn't be very applicable, this framework, or could you...
No, that's right. I mean, then I think then this would be more related to the literature on pseudo panels. Yeah. And then we have to think how to create a linkage, right? This is all about repeated measurements about a given unit. If we don't have the repeated measurement, we would need to kind of make sufficient assumption that kind of mimic a multiple measurement aspect. So I don't know actually how that would work out. I think this is much more about data, could be panel, but it's not necessarily actually over time, right? The point is that it's across outcomes. This is really what matters here. It might be that I just have a cross-section, a single cross-section, but I have lots of measures. This type of settings happen, for example, in the psychometric literature or in the work by Jim Heckman on unobserved skills, right? Latent skills, where we have a measurement system. That measurement system can be over time or could be cross-sectional. The point is that you need to have lots of outcomes. This is really what the group fixed effect approach will require. Not to have only repeated measurement, but quite a large number of measurements that allow us to get these types with reasonable accuracy.
Yeah.
Do these methods apply also for static models in which we still have a panel? Like imagine we want to estimate this unobserved heterogeneity, but in a static setting. Is this inapplicable?
Absolutely. In a way, the dynamic assumptions are just stronger, but just saying that this is static. So yeah, we can use this, and this is actually, this is not rare actually that people think about like repeated choices. For example, we still have a panel dimension in the data, but the model is not dynamic, and we just have like each period everybody redoes the choice, and that would be perfectly fine because we would get this multiple measurement aspect, and we could be able to pin down the distribution of types or the type, depending on the method that we use. Yeah.
I think on this, there is a recent paper by Jean-Marc Robin and Thomas Preda and a few others, I think, on having a static model, like repeat a static model where you still have panel data, where you do exactly this.
Yeah,
And
yeah,
this
yeah.
also allow them to identify continuous types. I saw it presented at TSE, but
Oh, yeah, yeah, and I saw the paper as well on continuous types. Yeah, yeah, no, I agree. I mean, then the issue is you need then quite a lot of structure with continuous types in order to be able to do
yes,
something.
yes,
Yeah.
yes.
So that's kind of the price to pay. I mean, the discrete type assumption, I think this is an interesting setting really because of this ability to capture multidimensional heterogeneity.
Yeah.
You know, in a way, the way a small number of types approximates a continuous heterogeneity becomes worse and worse as the dimension increases, right?
Yeah.
You know, to get an intuition, if you have just heterogeneity on a segment, right, on a line, on a segment, then with 5 types, maybe you can get a very good approximation already. But then if now your heterogeneity is on a square, with 5 types, it would be harder to where do you put the types exactly to get a good approximation? And then if you now have a cube, putting your 5 types will explain much less, you see? So this is really this, and this kind of decrease, right, in the convergence rate is formally it's actually exponential. So the difficulty of approximation becomes exponentially worse as the dimension of heterogeneity increases, which means that in a way, a practical approach is to be very dogmatic about the fact that there are finite number of types. You know, when you talk to structural people, I've seen this argument, we think of the types as approximations. I think there's a little bit of a tension there. You know, there are approximations, perhaps, but if we want to think of them as real approximations, then we need to commit to low-dimensional heterogeneity. We cannot have both. So either we are very religious about discrete types, or the dimensionality of heterogeneity, which means, for example, we say risk aversion is heterogeneous, but nothing else.
Stephane, I don't know if you, this audio here in the back of the room. There is a paper that looks at continuous types that, jives with a few things you mentioned. What you said is completely right, but the students may be interested. There's a paper by Neville, Turner, and Williams, which has continuous times in a dynamic programming discrete choice. I think they're looking at broadband choice, and it jives with the EM algorithm because it looks a lot like the grid. Next grid is step.
Yeah.
We put things on the grid, so we may want to check that paper as well.
Yeah, that's nice. No, I didn't know the reference. Thanks.
Yeah, feel free to send the reference so that we can see.
I can send the reference. I'll send it to you.
I'll put it in the chat. Any other questions? Well, join me in thanking Stephane for a wonderful lecture.
Thank you very much, and apologies again for not being there. Hope to see you all soon in person.
No. So we continue at 11, as far as I can see on the updated schedule. Let's take some time for a coffee break. You're in Europe, right?
In France, yeah.
In France, yeah. She's in France.
I was worried you were giving a lecture at 4 a.m. in Chicago.
Oh, no. I had to leave for France for some emergency.